In this video, I want to give a simple definition or intro into derivatives. I don't want to get into the heavy-duty limit as h approaches 0, blah, 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 all that stuff. We'll get into that. But right now, I want more of a touchy-feely kind of definition. A derivative is the slope of the curve. We get this by looking at the tangent to the curve at that point to figure out what the derivative is at that point. If the function is f of x, we can denote the derivative as f prime of x. So let's just grab a point. Put a tangent there. We'll call that point A. Now the graph is going up. The green line has a positive slope, so we know that the derivative is positive at that point. F prime of A is greater than 0. Let's look at another point over here. So this is an obvious negative slope. Let's say that this is point B, so we know f prime of B is less than 0. Another obvious point we would like to check are the flats. When you have a flat, the derivative is 0. At this point, we've got a horizontal tangent. I'm going to call that point C. So I see that f prime of C equals 0. A lot of what we'll be doing in the future is looking for where the derivative equals 0, because that's where you maximize profit or minimize costs or all this kind of good stuff. Let's see if we can find the derivative of a function. Just estimate. I'm going to estimate the slope of this function at 3. So I'm looking at f prime of 3. I want to estimate it. So I'm going to draw a tangent at that point. I drew it a little bit extra long so I could deal with the graphs and figure out what the height and the width of this triangle is. So the slope is change in y over change in x. This is obviously going down, so it's going to be negative 1.4 over 2. When I simplify, I get 0.7. So how do we interpret what we have? If I've got some funky function, I want to figure out what it actually means for f of 5 to equal 7 or f prime of 10 to be negative 12. Suppose we have this bizarre function, chaos to coffee conversion rate. This function computes how many cups of coffee you'll need to deal with the chaos, given that you have so many ounces of spilled glitter. I imagine someone working at a daycare center and the kids are just little monsters and they're spilling glitter, and that's how much you want to drink coffee. But personally, I might put a little whiskey in the coffee if it was that bad. But, well, one possibility, you always will probably need a little bit of coffee to start off with. As more and more glitter gets spilt, you may want to have more coffee. Maybe you don't give a shit. You just want your coffee. You don't care if there's any glitter going around. You're just going to drink your coffee and be fine. Or maybe you're just tired. It doesn't matter. At the very beginning, when the first few ounces are spilt, you get frustrated. But then after a while, you don't care. You're just taking it as it goes. So let's break this down more. The units for the derivative are going to be cups of coffee per units of glitter. Now if I say f of 12 is 5, that means if there are 12 ounces of spilled glitter, you'll need 5 cups of coffee to cope. If I say f prime of 6 equals 3, okay, so 3, it's 3 cups per unit of glitter. Keep in mind that 3 is the derivative, so it's 3 cups per unit of glitter. If there are 6 ounces of spilled glitter, just 1 more ounce, and you'll need 3 more cups of coffee. Let's look at another one. The amount of light intensity, measured in lux, at a certain lake is a function of depth, measured in meters. So you've got a lake, and right at the surface, f of 0 is 12. So the surface of the lake, the light intensity is 12 lux. As you go further down, the light can't penetrate through the water, so f of 25 might be 8. So at 25 meters, the light intensity is 8 lux. If f prime of 50 is about negative 0.07, it's negative because the light intensity is going down. And so looking at my units for the derivative, lux per meter, that means I've got negative 0.04 luxes per meter, which means at 50 meters you are losing 0.07 lux for every 1 meter. Or you're losing 7 lux for every 100 meters. When you are interpreting derivatives like this, always put your output units over your input units, and that's what you want to incorporate when you do your explanation. Say 1 more of the bottom thing, so just 1 more of the bottom thing gives you the derivative of the top thing. That's not very clear. We'll do more in class and it will make more sense.